Hey everybody, welcome to class 113. We are in the same unit, but we're starting a brand new topic within that unit. It's actually closely related, and it's actually pretty closely related to some things we've done earlier in the year. We're going to deal with a lot of analogies today. So if you look at the do now, there's do now part 1 and 2. I'd like for you to try those on your own, but just let me tell you what you're looking at. On the right here, this is a ball on a hill. Let me turn this on. This is a ball on a hill right here. Okay. And at the bottom here, you just have two charged objects. One is negative, it is stationary. The other is positive, it is free to move. Okay, so try the do now and pause the video, and then I'll go over it. All right, so hopefully you gave that a try. Number one says, answer the following questions using the image to the right. What will happen when you let go of the ball? Oh, look at the little red ball there. Hopefully you don't need to be in physics class to tell me that the ball is going to roll down the hill. Okay, you could say that as, go down the hill, whatever you want to say. This is because it has what type of energy at the top of the hill? If you recall, that's potential energy. What type of energy will this be turned into when it begins to move? So when things move, what kind of energy is that? Kinetic. And this one's a little bit trickier, but there's a physics word for this. If the ball were sitting at the bottom of the hill, so let's say we took the ball and the ball were now at the bottom of the hill. Okay, let's say it was down here somewhere. All right. If the ball were sitting at the bottom of the hill, what would we need to do to bring it back up the hill? Now, there's a few ways you could say it. You could pick it up. You could push it. Either way, what you have to do, and this is the important part, you have to apply a force over a distance. What do I mean by that exactly? If the ball were down here, you have to push it upward. So you have to apply force to move it a distance, over a distance to bring it back up there. All right, if at any point you stop applying that force, it's not going to go up any higher. Okay, what do we call that when we apply a force over a distance? If you recall, that is going to be, and this is actually the answer I really wanted you to put here. So what do we need to do to bring the ball back up the hill? We need to, big asterisks, do work, right? Work is force times distance. So maybe I'll write that down too. So there's a lot of stuff I'm writing in here in the margins. Work is force times distance. All right. We'll talk more about that in a second. So now we have an analogous situation. It says answer the following questions using the image to the right. The large charge is stationary. The small charge is free to move. Where would the little charge move? Well, the little charge is positive. The big charge is negative. So where would the little charge move? It's going to move toward the big or negative charge. This is because it has what type of energy? You might not have thought about it this way, but what it has is potential energy, not any type of potential energy, that positive charge. That positive charge has electric potential energy. What kind of energy is this turned into? It's still, you could just say electrical energy. You could say electrical kinetic energy, right? Because as it moves, it turns into kinetic energy. Now, if the little charge were right next to the big charge, okay, so imagine that positive charge is right next to the negative charge. What will we need to do to move it away from the big charge? You guessed it, you have to apply a force and you have to do work. Okay, apply force over distance. All right, So why did we do this analogy? I think this analogy is really good for talking about and starting to talk about what is electric potential. We know what potential energy is in terms of objects going down hills, objects that are up in the air, but objects that, in terms of electrical potential energy, it's basically the same thing. Objects with mass have a tendency to be attracted toward Earth. Objects with charge, or opposite charges in this case, have a tendency to be attracted toward each other. Okay, so just keep that in mind as we talk today, and we'll kind of go through it. We'll bring up this analogy constantly today. So, starting it here, we have a couple images. It says, as we lift objects up, we increase their gravitational potential energy. We do work on them. Right? Remember, work equals change in energy. And we do work on them because we apply a force over a distance. All right, just check out the image here. In this image, we increase gravitational potential energy when we move an object away from Earth, right? If you pick something up, you increase its potential energy. Over here, think about instead of the Earth, we have a big negative object, and instead of a massive object, we have a positive object. We increase the electrical potential energy when we move a positive object away from a negative, because if we let go of that positive object, it's going to fall back to the negative, right? Just like if we let go of this object here, it's going to fall back down to Earth. Different to think about, but it's very similar for our purposes. So number 4 says, as we move oppositely charged objects away from one another, or toward one another if they're like charges, we must apply a force over a distance. Think about that again. As we move oppositely charged objects away from one another. So if you move a positive away from a negative, so if you have a positive and a negative, to move them away from one another, you have to apply a force, right? Because generally, if you just let go of these two objects, they're going to go right to each other. But instead, to move them away, you have to apply force. Okay, they're kind of fighting that. Okay, you do work in that case, and you increase the potential energy. Okay, because you're fighting against the natural tendency. Now, let's say they were like charges. I'll start them off right here. What are these two objects going to do when you let go of them? They're going to have a tendency to move apart, right? So, if you apply an outside force, you move them towards each other, right? If you're pushing, it requires force to push them closer together. So since you're applying a force to get them closer together, you are doing work. You are increasing the potential energy of the system. In this case, electrical potential energy. All right? So basically, whenever you fight nature's natural tendency, you do work and you increase potential energy. Right? If you pick up an object, it doesn't want to get picked up, it wants to fall. So picking it up increases gravitational potential energy. If you move two positive objects toward each other, they don't want to do that. You're fighting their natural tendency to go apart. So since you're fighting the natural tendency as you bring them together, you increase potential energy. If you have a positive charge and a negative charge, what's their natural tendency? It's to come together. If you pull them apart, that's fighting their natural tendency. Therefore, you increase potential energy. Tough to think about. I want you to think about these scenarios below in number 5 before I do them. But it says if you apply an outside force to move the objects, you increase potential energy. So if you have to apply a force to move them, okay, if they're not going to move on their own, then you have to increase potential energy. So try these on your own, see if you're increasing or decreasing potential energy. All right, hopefully you tried all of those. So let's see. The first one says, if you move a positive charge away from a negative charge, you blank potential energy. What do positive and negatives want to do? They want to move toward each other. You're fighting that. You're moving them away. So you increase potential energy. Again, if you fight the natural tendency, you increase potential energy. If you move a positive charge toward a negative charge, you blank potential energy. Well, what do positives and negatives want to do? They want to move toward each other. Okay, so you're not fighting natural tendency, so you're decreasing potential energy. If you move a positive charge away from a positive charge, you blank potential energy. So what do positive charges want to do to other positive charges? Okay. They want to move away from each other, right? They want to repel. So you're not fighting the natural tendency, so you're decreasing. If you move a positive charge toward a positive charge, well, what do positive charges want to do to positive charges? They want to move away from each other, like charges repel. Therefore, you are fighting the natural tendency, you are increasing potential energy. For C and D, you could have just replaced the word positive with negative, and they would have worked out the same way. Hint, hint for the exit ticket on the Google form. All right, so we have an equation on our reference table that talks about electric potential. What is this? So electric potential is actually voltage. Okay, you've all heard of voltage before. If you use like a drill, okay, so today I was doing some stuff with the deck, and I was using a 20-volt power drill. Okay, voltage, it's the same voltage that we're talking about here. It is potential. So when you have a piece of electronic equipment, let's say it's a 20-volt drill, okay, that tells you about the amount of energy it can supply. All right. It's a little bit more complicated than that. We'll talk more about it when we get to circuits, but that's the idea. The more voltage, the more energy you can give something. Electrical energy, that is. Okay. So here's our voltage equation right from the reference table. Where is it on the reference table? I think it is, let's see. Scroll, go to electric stuff. There it is. V equals W over Q. I don't know what that means. Yes, you do. Look here. V, potential difference, or voltage as we call it. W, work, or electrical energy. And Q is charge. All right, so this is potential difference measured in volts. I can't spell. Difference. Okay, or voltage measured in volts, capital V. That one's easy to remember. This is work or electric energy. Not work of, work or electric energy. Measured in joules, right? And Q is, of course, charge measured in coulombs, capital C. Another unit for, excuse me, there's something on my iPad. All right. Another unit for voltage or potential difference is joules per coulomb. I don't really use that, but you might see it as an answer choice on like a standardized test or something. But generally, potential difference is measured in volts. So, just to reiterate from our analogy in the do now, voltage is the hill. Okay, the bigger the voltage, the bigger the hill. Okay, so if something has a lot of voltage, think about it being a really big hill. Bigger hill leads to the ball having, so bigger hill or voltage leads to the ball or charge having more energy, or having more, I'll just say more energy. Potential, which turns into kinetic. So the work is the energy needed to get the ball up the hill, or the energy gained as the ball goes down the hill. Work is also the energy needed to bring the positive charge away from the negative charge, okay? Or the amount of energy it gains as it moves towards, the amount of kinetic energy it gains as it moves back towards the negative charge. And charge is like the ball, okay? The heavier the ball, i.e. more charge, requires more work or more force, I will say more work, to move up the hill, and has more energy when it moves. Okay, if you recall, potential energy is mgh. More mass, more potential energy. This works the same way. In this case, energy, W, equals V times Q. More Q, more charge, means more energy. All right. So let's we'll do a lot of this stuff when we get into circuits, but I think this is a good analogy to use. That voltage is like a hill, and massive objects on the hill are like charges on the hill. Okay. All right, let's do some math problems here. So we have one equation, V equals W over Q. let's see what we can use here. So it says how much energy. So that's, be careful, it's not E here. It's actually W we're going to use for energy. Okay. How much energy does an electron, so we know Q. That's on our reference table, right? An elementary charge. Acquire from 1 volt battery. V equals 1 volt. Okay, so V equals W over Q. Let's see, 1 volt equals W over 1.6 times 10 to the negative 19 coulombs. Cross multiply here, and the amount of energy you get here is 1.6 times 10 to the negative 19. Our units for work are joules. All right. Make sure you're able to do this on your own, but I'm kind of skipping the math for now. All right, if we look at the next one, it says, how much work is required to move 3 coulombs of charge? So we're looking for work again. Q is 3 coulombs through a voltage of 9 volts. All right, so V equals W over Q. All right, so let's see. V is 9 volts. W is unknown. Q is 3 coulombs. Cross multiply, you get 27 joules. All right, a potential difference of 10 volts, so that's our voltage, exists between 2 points A and B within an electric field. What is the magnitude of charge, so looking for Q, that requires 2 times 10 to the negative 2, excuse me, 2 times 10 to the negative 2 joules of work to move from A to B. All right, so let's just solve for the unknown again. W equals, also made a mistake there. V equals W over Q. Let me just fix that Q. All right, V is 10 volts. W is 2 times 10 to the negative 2 is 0.02, I believe, joules over Q. All right, so then we have Q equals 0.002 coulombs. Just make sure that's right. I think that's right. All right. The next one here, if 60 joules of work, so there's our work, is required to move 5 coulombs, that's Q, of charge between 2 points in an electric field, what is the potential difference between these points? So we're looking for V, right? V is potential difference. So V equals W over Q. V equals 60 joules over 5 coulombs. And the voltage is going to be 12 volts, or 12 joules per coulomb. See how you could see the joules per coulomb there, joules over coulombs, but 12 volts is fine to write. So just to wrap it all up, work or energy is required to move a charge across a potential difference up the hill. A charge that is moved by a potential difference gains energy. Okay, so if you learned nothing else today, here's what I want you to make sure you understand. Voltage is potential difference. Okay, same term. Potential difference gives charged potential difference gives charged objects energy. Okay, just like hills give massive objects energy when they're on the hills. So if a charged object is in a potential difference, it gets electric potential energy. If a massive object is on a hill, it has gravitational potential energy. Okay? Voltage is like electricity's hill. Okay, that's one way to think about it. All right, so number 13 says, we'll see next chapter, voltage from a battery gives electrons energy as they move through a circuit. The more voltage in a battery, the stronger the current. All right, kind of goes with the what we've been talking about today. All right, everybody, so don't forget to fill out the Google form. We do have class for the rest of the week. Don't forget that. We have class Wednesday, Thursday, and Friday. Spring break was entirely canceled, not just through Wednesday. All right, if you have any questions, stop into Extra Help.